All right, in this video, we're going to be talking about Dalton's law and the ideal gas law. Now, both of these are very, very important, so we're going to have a lab over these because they're so important. So, Dalton's law. Dalton's law is about partial pressure, and what it means is it states the pressure of a mixture of gases is simply the sum of the individual pressures of each of the gases known as partial pressure. So, the air that you breathe, or the air that you're around, has a bunch of different gases that exist. If I add up the pressures of every single one of those gases, they should total up to STP, the standard pressure here, which is 101.3, so this must be in kPa. And so if I add up all these kPa's over here, they should equal up to 101.3 because that's what air is. And so here's my equation that you should write down. P total is equal to the pressure of the first gas plus the pressure of the second one plus the pressure of the third one, and so on and so on and so on. So in this question, it says a 5-liter container at 20 degrees Celsius has 4 gases pumped into it. So P total is equal to the pressure of the first gas, the pressure of the second gas, the pressure of the third gas, and the pressure of the fourth gas. The total pressure of the gases is 4.8 atm. If the pressure of the first gas is 1.2 atm, and the pressure of the second is 0.49 atm, the pressure of the third gas is 0.78 atm, what is the pressure of the fourth gas? All you need to do is just plug it in and solve. So the total pressure here would be 4.8 atm. That's equal to the pressure of the first gas, which is 1.2 atm, plus the pressure of the second gas, which was 0.49 atm, pressure of the third gas, 0.78 atm, plus the pressure of the fourth gas. Notice that they are all atm. They have to be the exact same pressure in order to use this formula. And so to solve for the pressure 4, all you need to do is add these 3 up and then subtract by 4.8. So 4.8 minus 1.2 minus 0.49 minus 0.78, and I got 2.33 atm. And that is the pressure of my fourth gas right there. In this question, it says a container has oxygen, xenon, helium in it. Its total pressure is known to be 972 torr. If the pressure of the helium is 0.458 atm and the pressure of the oxygen is 74.1 kPa, what is the pressure of xenon in torr? Since they want to know what's the pressure of xenon in torr, everything has to be in torr. So if it's not in torr, you have to convert it. So let me write my equation. P total is equal to the pressure of the first gas, which is oxygen, so I'm going to put O2 there, plus the pressure of my next gas, which is xenon, Xe, and helium, He. All right, if everything has to be in torr, the total pressure, if you look up here, is already in torr. So I just plug it in, 972 torr. Okay, because it's already in torr, I can plug it in, is equal to the pressure of oxygen. Where does it say oxygen? Right here. Oxygen is 74.1 kPa. This is not torr, so I have to convert it first. So 74.1 kPa. And I'm going to change it to torr. So kPa at the bottom, torr at the top. 101.3 kPa, 760 torr. Plugging it in because this will cancel out. So 74.1 divided by 101.3 times 760. I got 556 torr. So I'm going to plug it in for oxygen, 556 torr. There's that one. Plus the pressure of xenon. We don't know what that is, so I'm going to leave it Xe because that's what I'm trying to figure out. What is the pressure of this? Plus the pressure of helium. So if I look, helium is right here. No, well, there should be an L somewhere in there. Helium is 0.458. So that's not in torr, so I got to convert it. So 0.458 atm. I'm going to go from atm to torr. 1 atm is 760 torr. So this will equal, if I plug it in, I got 348 torr. And so I'll put it in here, 348 torr. All right, solving for my missing one, I would add these two up over here, and then I'm going to subtract by 972. So the pressure of xenon is going to equal, once I do that, 972 minus 556 minus 348. I got 68 torr. So less than the others, but it still has a pressure. And then it says a mixture of three gases is known to have a pressure of 1.27 atm. If two of the gases have the same partial pressure and the pressure of the third gas is 650 torr, what is the pressure of each of the other gases in torr? So again, they want my answer in torr, so I need to make sure all my pressures are in torr. So P total is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas. This one and this one equal each other because it says that the two gases have the same partial pressures. So since they have the same partial pressure, I can do this then. P total is equal to, let's make up a new pressure, pressure X. 2 pressure X, which is equal to pressure 1 and pressure 2. It'll equal both of them. Plus pressure 3. Pressure 3 is already in torr. It says it right here, 650 torr is for the third one, so I'm going to plug it in. The total pressure over here, though, is not in torr, it's in atm, so I have to convert it. So 1.27 atm, I'm going to convert it to torr. 1 atm is 760 torr. Plugging it in, 1.27 times 760 gives me 956. Oh, I'm sorry, 965. Sorry, read that wrong. Torr. So that's my total pressure, 965 torr. It's equal to 2px plus 650. All right, so then you just have to do a little algebra here. I'm going to subtract first, so 965 minus 650. And I get 315 is equal to 2 pre-x. And so to get the pressure of pressure 1 and pressure 2, I just need to divide by 2 on both sides. And so pressure X, or pressure 1 and 2, is equal to 158, since I want 3 sig figs, torr. And so there's my answer for this one. So our lab is going to look kind of like this, where we have a reaction over here, and it's going to react, and when it's reacting, it's going to produce some gas. Those gases are going to travel just like so, and I'm going to collect the gas inside of a, this one's collecting it in a test tube. We're going to be using a different instrument whenever we're doing ours. But basically, you can trap gas up here, and then I can measure the gas that's being produced. So it's a special type of Dalton's law. So it's kind of like the same thing where I have the total pressure, but there's only two things that have a pressure. The pressure of the gas molecules that are, oh, sorry, I don't know what happened here. The gas molecules that are inside there, and the pressure of the water that's being pushing up against the gas. Both of those things are exerting a type of pressure. So water has different pressures depending on the temperature, because you've got to remember, if I increase the temperature of water, it's going to boil. So at 100 degrees, when it starts boiling, it has a pressure of 760 because all of it's turning into a gas. So the warmer it gets, the higher the pressure. The cooler it gets, the lower the pressure of the water. So let me show you how it works. It says a sample of hydrogen gas is collected over water. So there's my word, something that is collected over water. So I'm going to be using this equation. P total is equal to the pressure of the gas plus the pressure of water at 14 degrees Celsius. The pressure of the resultant mixture is 113 kPa. Okay. What is the pressure that is exerted by the dry hydrogen alone in kPa? So right here, 113 kPa, this is the resultant mixture. This is the total. 113.0 kPa is equal to the pressure of the gas, this is what I'm looking for, plus the pressure of water. The pressure of water at 14 degrees is 12 mmHg. Now remember, I can't plug this in because it says mmHg and I need it to say kPa. So I'm going to change it real quick. I'm just going to convert it, mmHg to kPa, 760 to 101.3 kPa. Multiplying and dividing, I got 1.60 kPa. So I'll plug it in here, 1.6 kPa. I'm going to subtract in order to get to the pressure of the gas. And so if I subtract the pressure of the gas, or the hydrogen in this case, is equal to 113 minus 1.6, and I get 111.4 kPa. And that is the correct answer right there. All right, try pausing the video and try doing this one by yourself, okay? Okay, on this one, you should have got P total is equal to the pressure of the gas plus the pressure of water. The total pressure in this one was 78.4, oh, sorry, 0.5 kPa. I want to know what's the pressure of the gas plus the pressure of water. You should have converted it, 10.5 torr. 760 torr at the bottom, and you should have got 101.3 kPa on the top. If you plugged it in, I got 1.40 or 1.4, so 1.4 kPa. If I would have subtracted, the pressure of the gas is equal to, sorry, 78.5 minus 1.4, and I got 77.1 kPa. And there's the answer right there. All right, try doing this last one by yourself. Okay, and you should have got this. The pressure of the gas is equal to 0.608 atm, and that is the pressure of my gas only. All right, so in order to do the lab, we have to learn one more section. So I'm going to go over the ideal gas law. Now this is by far the most important equation in this entire unit. So make sure that you're writing these down and you got this section down. All right, the first thing is the ideal gas law. So it is equal to PV is equal to nRT. I like to call it PIV-NERT. So PV equals nRT, where P is the pressure, and I want to change it to make sure that it's atm. If it's not, then I can just do an extra step to change it. V is the volume, and it's usually in liters, but again, I can change it if it's milliliters. N is the number of moles, which is also equal to the number of grams. Remember, I can change grams to moles. R, this one's new. R is the gas law constant. R is basically just to make sure that the pressure and the volume equal the moles and the temperature. If I multiply by this specific number right here, it will always equal each other. So that's why we call it the gas law constant. It's a pretty long unit over here, so we're going to need to memorize this one, or at least know how to use it whenever we're doing our problems. 0.0821 liters times atm divided by moles times Kelvin. And last, T is temperature, which is the units of Kelvin. So let me show you how PIV-NERT works. It says you fill a rigid steel container that has a volume of 20 liters, so this would be a volume, with 40 moles, that's an N, of nitrogen gas at 28 degrees. There's a temperature. If I add 273, because remember you cannot use degrees Celsius, you should get 301. Kelvin. What would the pressure be in kPa? I got to make sure I put kPa as my final answer. So we're going to be using our new equation, Pivner. In this one, I'm looking for a pressure, so I'm looking for pressure. So I'm going to divide by volume on both sides to get it by itself. So the pressure is equal to nRT over V. I'm going to set up a table. I'm going to put N first, so that would be 40 moles. R is next, that's the gas law constant. R always needs its own column, and I'm going to show you why. So let me draw all of R. It is 0.0821, and it said liters times ATM divided by moles times Kelvin. All of this is letter R. So that's why R needs its own column, because it needs to look like that. T is the temperature. That goes right here, 301 Kelvin. There's my T. And then my volume, I can put it in the first box or the last one or make a new one. It doesn't matter. I'll just put it here in the first one. It'll be 20.0 liters. If I look at my units, the L's cancel out, the K cancels out, the mole cancels out. All I'm left with is ATM. But remember, we wanted our answer in kPa, so we're going to do one more step, and we're going to change ATM to kPa. 1 ATM is 101.3 kPa. Now ATM cancels out. I have kPa left, and that's my final answer, so we're done. Multiplying it, 40 times 0.08201 times 301 times 101.3 divided by 20. And I got 5,001 kPa. There's my answer right there. Let's try doing another one. You can pause the video if you think you're good at it. If not, just play the video so we can get our feet under us. So this one, let's label everything. How many moles, so looking for N, of oxygen must be put in a 500 milliliter flask. This is a volume at 20 degrees temperature at 273, 293 Kelvin. That has a flask of 1.77 ATM. This is a pressure. So writing Pivner, I am looking for moles. So since I'm looking for moles, I'm going to divide by RT. So I get pressure volume divided by RT is equal to N. Okay, it's looking good. Now we just gotta plug it in. Pressure goes at the top, so my pressure was 1.77 ATM. Times volume, volume was 500 milliliters. I'm probably gonna have to change this to liters, but we'll do that later. Divided by R, but remember I told you, R needs to have its own column, so I'm gonna put all of R right here. It is, since I'm dividing by R, the number is going to go at the bottom, 0.0821 liters times ATM divided by moles times Kelvin. Again, you need to be careful with those units. This is my R. I just had to put it at the bottom because I'm dividing by R. Divided by temperature, I put that also at the bottom, but I'll put it over here, 293 K. Now I'll cancel out whatever's all my units, ATM, K, and that's it. I'm left with liters, milliliters, and moles. I only want to keep moles because that's what I'm looking for, so I'm going to do one more step and get rid of the liters and the milliliters. Liters, milliliters. 1 milliliter is 1 times 10 to the negative third power. Now milliliters cancels out, liters cancels out, and now I only have moles left, so we're done. Now I can plug it in. 1.77 times 500 times 1e negative 3 divided by 293 divided by 0.0821. And the moles is equal to 0.0368 moles. And that would be my answer right there. You just have to keep track of your letters, make sure everything's canceling out, and you should be fine. All right, try pausing the video and try doing this one by yourself. If they're looking for grams, remember, then I'm going to go to moles, and then I'm going to change it to grams. All right, for this one, just start. All right, so Pivner. On this one, I'm looking for moles, which is N, so I'm going to divide by RT, just like in that last problem. So PV divided by RT is equal to N. Plugging it in, starting with the pressure, 3.41 atm times the volume, 0.500 liters, divided by R, which was 0.0821 liters times atm moles times Kelvin, and divided by temperature, which was 350 K. I don't need to change it because it's already in K. Canceling out my units, atm cancels out, K cancels out, liters cancels out. I'm left with moles, but they don't want moles, they want grams, so I'm going to go one more step and change it. Moles, grams. 1 mole is equal to the molar mass. They're talking about oxygen in this case. Oxygen, remember, is O2 because it's diatomic, so that would be 32 on the periodic table. 16 times 2 would give me 32. Now moles cancels out. I have grams. I just plug it into the calculator. 3.41 times 0.500 times 32 divided by 350 divided by 0.0821, and I get 1.90 grams. And there we go. And the last one, try plugging it in, see what you can get, and if you get the answer right, then you can stop the video. If you don't, then watch me solve it, and I'll give you a second. All right, you should have got D. If you got 41.8 atm, then you're good. You can stop the video and go work on the practice. If not, watch the video and let's see where you went wrong. So I have Pivnert. I'm looking for the pressure, so you should divide it by the volume on both sides. So pressure is equal to nRT over V. N in this case, I don't have N, but I have grams, which is related to moles, so 36 grams. R, we know R, 0.0821 liters times atm, moles times Kelvin, times temperature, which was 283 Kelvin, because you should have added 273, and divided by volume, which was 5 liters. I'll put it over here, 5.00 liters. Canceling out all my units out, K cancels out, liters cancels out. That's pretty much it. I want ATM left over, so I need to get rid of moles and grams. So I'm going to go one more step. Moles, grams. 1 mole is equal to grams. Helium on the periodic table, I think, is 4.00. Canceling all my units out. Grams cancels out. So does moles. I'm left with ATM. Plugging this in, you should get letter D. And you should be good to do the practice now.